The stars you see at night are not the present, they are the past. Some of them no longer exist. Yet their light is still arriving long after they are gone. This simple fact hides a deeper truth that most people never think about. Everything you can see, touch, or measure may not be the full story of reality. There is a point in the universe where even light gives up its message, a boundary where information stops reaching us. Scientists call this the observable limit, but the name is misleading. It sounds like a simple edge. In reality, it may be the edge of everything we will ever know. Beyond that boundary, space does not end. It continues. Galaxies may still exist. Stars may still burn. Entire structures larger than anything we can see may stretch outward into darkness. But none of it will ever send us a signal. Not now. Not in the future. Not in any time we can reach. This is where the idea of the edge of reality begins to change. It is not a physical wall. It is not a border you could cross. It is a limit defined by light, time, and the structure of the universe itself. And yet it creates a powerful illusion. It makes a part of existence completely invisible, as if it does not exist at all. In modern physics, reality is defined in a very strict way. It is everything that can be observed, measured, and described through mathematics. If something cannot interact with us in any form, it becomes impossible to confirm. It may exist or it may not. From a scientific point of view, it is beyond reach. This leads to a disturbing idea. The universe we call real may only be a small region inside a much larger system, a cosmic bubble formed by the limits of light and time. Inside this bubble, physics behaves in consistent and predictable ways. Outside it, the same rules may apply or they may not. We simply do not know. Even the most advanced theories in cosmology suggest this limit is unavoidable. The universe has a finite age, around 13.8 billion years. Light has only had that much time to travel. That means there is a maximum distance from which any information can ever reach us. No telescope can extend that boundary. No technology can break it. It is built into the structure of existence itself. This creates a strange situation. We often think of science as something that keeps expanding knowledge endlessly. But at the largest scale, there is a hard stop, a point where the universe becomes silent, not because nothing is there, but because nothing can reach us from there. And yet, beyond that silence, reality may continue. The same laws of physics may still operate, or completely different laws may take over. Some regions may be filled with galaxies. Others may be empty. Some may never have formed stars at all. All of it could exist, but remain forever disconnected from us. This raises a deeper question that physics cannot easily answer. Is this boundary the true edge of reality, or is it only the edge of human perception? Because everything we know about the universe comes through signals: light, radiation, gravity waves. If something cannot send any of these signals to us, it becomes invisible in every practical sense. But invisibility does not mean non-existence. It only means separation. This is where the mystery begins to grow. The universe may not be a single connected whole in the way we think. It may be far larger, possibly infinite, with regions forever isolated from each other. Each region living inside its own horizon, its own observable limit, its own version of reality. Even time itself becomes part of the boundary. We are not only limited by distance, we are limited by history. We can only see as far back as the universe allows light to travel. Before that, everything is hidden behind a dense wall of early cosmic conditions. A moment so extreme that even photons could not move freely. So when we speak about reality, we are not speaking about everything that exists. We are speaking about everything that can reach us. That distinction may seem small, but it changes everything. In this video, we will go deeper into that boundary. We will explore how modern physics defines the limits of observation, where space-time begins to break down, and why some scientists believe reality itself may be far larger and stranger than anything we can ever measure. We will also look at ideas that challenge the very meaning of space, time, and existence. Because at the edge of reality, the rules we rely on may no longer hold. And what lies beyond may not just change science. It may change the way we understand existence itself. Welcome to the channel. If you want to explore the deepest mysteries of the universe, subscribe now and stay with us till the end. Light is not instant. It moves at a fixed speed, around 300,000 kilometers every second. That number sounds huge, but in cosmic terms, it is slow. When we look at distant space, we are not seeing it as it is now. We are seeing it as it was when the light first began its journey. This creates a natural limit, a boundary in time and space, because the universe has an age, around 13.8 billion years. Light has only had that much time to travel since the beginning. That means there is a maximum distance any signal can reach us from. This limit is called the observable universe. It is not defined by walls or edges. It is defined by time. If light has not had enough time to reach us, we cannot see it. No matter how powerful the telescope becomes, it cannot change this rule. At the farthest edge of what we can observe lies a strange region. The light coming from there is older than almost anything else we can detect. It comes from a time when the universe was still forming its first structures. Even that light is stretched and weakened after traveling for billions of years through expanding space. Beyond that region lies a boundary known as the cosmic horizon. This is not a physical surface. It is a limit created by expansion and time. Beyond this horizon, light from distant regions has not reached us yet. In fact, some of it never will. The universe is expanding, not like an explosion into empty space, but like space itself stretching. As space expands, distant regions move away from us faster and faster. Some galaxies are already crossing a point where their light will never reach Earth, no matter how long we wait. This creates a powerful divide. On one side of the horizon is everything we can ever observe. On the other side is everything that exists but remains permanently hidden. There is no communication between these regions. No signal can cross this boundary once it passes a certain distance. This is where things become even more unsettling. The cosmic horizon is not fixed in place. It depends on time. As the universe expands, new regions slip beyond reach. At the same time, some ancient light still arrives from far away, giving us a fading window into the deep past. A lesser-known fact is that the observable universe is not centered on Earth in any special way. Every observer, no matter where they are, has their own observable universe. Each one is centered on their position. This means there are countless overlapping bubbles of observation across the cosmos, each with its own limit. Inside our bubble, we see around 2 trillion galaxies. That number is already beyond human scale. Yet scientists believe this may be only a small fraction of the full universe. Some models suggest space could extend infinitely, with galaxies continuing far beyond any horizon we can define. If that is true, then the universe we observe is not the universe as a whole. It is a local region, a small patch carved out of something far larger. A place defined not by boundaries in space, but by the limits of light and time. And beyond this patch, space may continue in ways that follow the same laws we know. Or it may contain regions so distant that their history, structure, and behavior will never influence anything within reach. For more than a century, physics has been built on 2 powerful ideas. One describes the very large. The other describes the very small. Both are extremely accurate. Both have been tested again and again. Yet both refuse to work together when pushed to their limits. The first idea comes from Einstein. His theory of general relativity describes gravity not as a force, but as the bending of space-time itself. Massive objects like stars and planets curve the fabric of space and time around them. Other objects move along these curves. This is how planets orbit, how galaxies form, and how black holes trap even light. On cosmic scales, this theory works with extreme precision. It predicts how light bends around galaxies. It explains the expansion of the universe. It even predicts time slowing down near massive objects. Satellites in orbit must correct for this effect every day. Without it, global navigation would fail. The second idea comes from quantum mechanics. This is the rule book of atoms and particles. It describes a world that is not smooth or predictable. Instead, it is uncertain. Particles do not have exact positions until they are measured. They exist in probabilities, not fixed states. Energy comes in tiny packets. Even empty space is filled with constant activity. Quantum mechanics is also incredibly accurate. It powers modern electronics. It explains how atoms hold together. It predicts results with extreme precision at the microscopic level. No experiment has ever broken its core rules. Yet here is the problem. When both theories are pushed into the same extreme conditions, they fail to agree. They give results that do not match. They produce equations that break down. They cannot describe the same reality at the same time. This conflict becomes most obvious in two places: inside black holes and at the very beginning of the universe. In these regions, gravity becomes extremely strong, space becomes extremely small, and quantum effects become extremely important. Inside a black hole, general relativity predicts a point of infinite density, a singularity, a place where space-time curves endlessly. But quantum mechanics says such infinity should not exist. It suggests that at small scales, space should behave in unpredictable fluctuations, not collapse into a single point. At the beginning of the universe, the same conflict appears. The Big Bang model describes a state where everything was compressed into an extremely hot, dense point. But when we apply both theories together, the math stops making sense. The rules of space-time begin to fail. A lesser-known detail is that time itself may lose meaning in these extreme regions. In general relativity, time is part of the same fabric as space. It bends and stretches. But in quantum theory, time is usually treated as something fixed in the background. When both collide, there is no clear agreement on what time even is. This suggests something deeply unsettling. Space-time, the smooth structure we rely on, may not be fundamental. It may only be an approximation, a surface-level description that works well in normal conditions, but breaks down when reality is pushed far enough. At extremely small scales, some theories suggest space-time may become grainy, not smooth, not continuous, more like a restless structure that constantly fluctuates. Distances may lose their meaning. Directions may stop being fixed. The very idea of here and there may no longer apply in a simple way. In these extreme regions, reality may stop behaving like a continuous stage and instead begin to behave in a way that is fragmented, uncertain, and unstable. There is a scale in physics where our normal understanding of reality begins to collapse. It is called the Planck scale. At this level, distances are so small that they are almost impossible to describe in familiar terms. Not because we lack tools, but because the meaning of distance itself starts to change. The Planck length is far smaller than anything atoms or particles can explain. It is the scale where gravity and quantum effects are expected to merge into a single unknown framework. No experiment has ever directly reached it. Yet many physicists believe it is the point where space-time stops behaving like a smooth structure. At everyday scales, space looks empty and calm. It seems stable and continuous. But quantum physics tells a very different story. Even in complete darkness, empty space is not truly empty. It is filled with constant activity at a microscopic level. Particles appear and disappear in extremely short times. Energy fluctuates without warning. This is not a poetic idea. It is measured in subtle effects. Forces between particles behave in ways that confirm this hidden activity. Space itself is never perfectly still. It is always in motion at a level far below human perception. As we move closer to the Planck scale, this motion becomes even more extreme. Space and time are no longer smooth surfaces. They begin to resemble something far more chaotic, a structure often described as quantum foam. Not foam in the everyday sense, but a constantly shifting fabric of space-time itself. In this state, distances may flicker between values. Time intervals may lose stability. The idea of a fixed background disappears. Space is no longer a quiet stage where events happen. It becomes part of the events themselves, constantly reshaping. A lesser-known idea in modern physics is that this foam-like structure may be unavoidable if quantum gravity is real. Some theories suggest that space-time at this scale is made of tiny loops or vibrating elements. Others suggest it is purely statistical, with no underlying solid structure at all. In all these models, one idea remains consistent. The smooth universe we experience may be an illusion created by averaging over countless tiny fluctuations. What looks stable from far away may be extremely unstable up close. At this level, the usual rules of space and time begin to lose meaning. The concept of a single location becomes unclear. The idea of a precise moment becomes uncertain. Even cause and effect may not behave in a simple linear way. Some approaches in theoretical physics suggest that below the Planck scale, asking about space or time may no longer make sense at all. Instead of objects moving through space, there may only be relationships between events, patterns of probability replacing solid structure. This leads to a deeper shift in thinking. Matter may not be the foundation of reality. Space may not be the stage. Time may not be the flow. Instead, everything may emerge from fluctuations that are fundamentally uncertain. In this view, the universe is not built from fixed pieces. It is built from possibilities that constantly shift. Stability is not absolute. It is temporary. And the deeper one goes into reality, the less solid it becomes until only the patterns of uncertainty remain. One of the most surprising ideas in modern physics is that reality may not be built from matter at all. Instead, it may be built from information, not physical objects, not solid space, but encoded data like a cosmic record written on a boundary that we cannot directly access. This idea comes from something called the holographic principle. It suggests that everything inside a volume of space can be described by information stored on its outer boundary. In simple terms, a three-dimensional world may be fully represented by two-dimensional data. This sounds strange at first. Space feels solid and real. Objects have depth, weight, and structure. But physics shows that many deep properties of the universe can be described in ways that do not require full three-dimensional information. Instead, the boundary of a region may contain all the information needed to describe what happens inside it. This idea is strongly connected to black holes. When matter falls into a black hole, it disappears from view, but it does not seem to destroy information. Instead, that information appears to be stored on the surface of the black hole, known as the event horizon. A lesser-known fact is that black holes are not just empty objects in space. They carry entropy. This means they have a measurable amount of disorder or information content. The amount of entropy is not related to their volume, but to the area of their surface. This discovery shocked physics because it suggests that the true information content of a region depends on its boundary, not its interior. This leads to a deeper question. If all information inside a region is stored on its surface, then what we experience as depth and volume may be a kind of reconstruction, a system that takes encoded data and translates it into a three-dimensional experience. Some theoretical models suggest that space itself may emerge from patterns of information, not as a background where information is stored, but as something created by it. Distance, shape, and even geometry may be secondary effects. The real foundation may be abstract relationships between bits of information. In this view, the universe is not a collection of objects sitting inside space. It is a network of encoded relationships. Every particle, every force, every event may be part of a vast informational structure. What we call reality may be the output of this structure, not the structure itself. This idea becomes even more interesting when combined with quantum physics. At the quantum level, particles do not have definite states until they are measured. They exist in probabilities. Some physicists suggest that this fits naturally with an informational universe, where outcomes are not fixed until information is updated. There is also a connection to entropy and time. The flow of time may be linked to the way information changes and spreads. As information becomes more complex and distributed, the direction we call time emerges. If these ideas are correct, then reality may not be fundamentally physical. It may be informational at its core. Space, matter, and even time could be secondary expressions of a deeper system that operates through encoding, transformation, and decoding of information patterns. This shifts everything that seems solid into something far more abstract. And it opens the possibility that what is seen as physical reality may only be one layer of a much deeper informational structure that defines everything we experience. In the earliest moments of the universe, something extraordinary may have happened. Space itself may have expanded at a speed far beyond anything we see today. This period is known as cosmic inflation. It is believed to have taken place in a fraction of a second after the Big Bang, yet it shaped everything that followed. During this phase, the universe grew from something smaller than an atom to a vast cosmic structure. Not by moving through space, but by stretching space itself. This rapid expansion smoothed out the universe and set the stage for galaxies, stars, and planets to form much later. But inflation may hold a deeper secret. Some versions of the theory suggest it did not stop everywhere at once. In some regions, it may have ended, allowing galaxies like ours to form. In other regions, it may still be happening even now, far beyond any possible observation. This leads to a far more extreme idea. If inflation continues in different regions, then new universes could constantly be forming, each one separated by expanding space that prevents any contact between them. These regions would not share signals, light, or information. This is where the concept of the multiverse appears. A collection of many universes, each existing in its own isolated region. Some may follow the same physical laws as ours. Others may not. The constants of nature could be different. Gravity could be stronger or weaker. Even the behavior of atoms could change. A lesser known aspect of these models is that they do not require a single beginning shared by all universes. Instead, each region of space could have its own origin point, its own timeline, its own evolution of physical laws. From the outside, there may be no single unified structure, only an endless process of universe creation. In this view, our universe becomes one bubble among countless others, a region where inflation stopped long enough for matter to form and complexity to emerge. Beyond our cosmic horizon, other bubbles may exist, each expanding into its own isolated reality. These bubbles would be forever separated, not by distance alone, but by the expansion of space itself. Even traveling at the speed of light would not allow contact between them. The gaps between them grow faster than any signal can cross. This creates a striking shift in perspective. The universe is no longer a single connected whole. It becomes a vast and possibly infinite collection of separate domains, each one self-contained, each one unaware of the others. Some theoretical models suggest that collisions between these bubbles may have left subtle traces in the structure of our universe. Slight patterns in cosmic radiation or unusual distributions of matter. These ideas are still being studied and no final evidence has been confirmed, but they continue to shape how scientists think about the largest scales of existence. If this picture is correct, then the edge of reality is not a boundary at all. It is a transition point, a place where one universe gives way to another. Not a wall, but a threshold where reality continues in forms that may be completely different from anything inside our own cosmic bubble. And beyond that threshold, the process may never end. Across every level of modern physics, a single pattern keeps appearing. The universe is always larger, deeper, and more uncertain than it first seems. From the cosmic horizon that limits what can be seen to the quantum foam that refuses to stay still, reality never settles into something simple. At the largest scale, light draws a hard boundary around what can be observed. Beyond it, galaxies may exist forever out of reach. At the smallest scale, space-time itself begins to break apart into fluctuations that do not behave like anything familiar. And in between, space and time may not even be fundamental, but built from information that we are only beginning to understand. Even the idea of physical reality starts to shift under this pressure. The holographic principle suggests that what we see as three-dimensional space could emerge from a deeper layer of encoded information. Black holes hint that the surface of a region may contain everything about its interior, and quantum physics shows that certainty itself may not exist until information is measured. Then there is the possibility that our universe is not alone. That cosmic inflation may have produced countless other regions, each forming its own isolated universe. Some may follow the same laws. Others may operate under rules completely different from anything we can describe. Together, they form a structure far beyond a single connected cosmos. All of this leads to a simple but unsettling truth. Physics is not closing the story of reality. It is opening it. Every answer seems to reveal a deeper question. Every boundary seems to point towards something beyond it. The edge of reality may not be a wall. It may not be an end at all. It may be a shift in understanding, a place where the idea of what is real stops being fixed and starts becoming something far more flexible and unknown. What we call reality may only be the beginning layer of something much larger, something that stretches beyond observation, beyond measurement, and possibly beyond complete understanding. If you enjoyed this journey into the deepest edges of physics and existence, take a moment to like the video and subscribe to the channel. There is still much more hidden in the universe waiting to be uncovered.